we shall still continue with the design of columns. So far we have done that axially loaded columns, and last class we have started uniaxial bending. Now let us see that how that if there is a moment acting on the columns in addition to besides axial load, then what happens. So if this is a column load P and moment M, what we can do, if we take a section, we shall get a cross section of the column. Not necessarily we shall make this column say square, we can make it rectangular also. If we have say axially loaded, then we can take it say, even we can take it say circular if it is required, square, it does not matter, rectangular also. When we are having say bending, so what we can do, we can provide that side that about the axis there are two conventions we generally follow. One is that whenever we specify moment, we say that about the axis, or we say that along the axis. That is the only say designation. Say mx, whenever we talk say mx, moment about x, or say moment, though we are specifying that means moment about y, but we are specifying that about x. So that way also we specify. So depending on the situation, say you are talking say moment this way. If this is your say x axis, I can say like this, because this convention should be followed and it should be mentioned. So if we take say this is your section, obviously you can say this is your x axis and this is your y axis. Now you will find out that people used to say mx, people used to say my. When we are talking say mx, so obviously the question arises whether that mx is about y, that means about y I mean to say about this particular axis, but it is acting about y. So that means as if it is along x. So other alternative also could be that about mx means about x, but it is acting that other direction. So this is the convention that it has to be clear. So let us say here whenever we are talking say this mx, my, all those things. So what we can do, if we talk, sorry, this is your y axis. So what we can do in this case, we can say mx, we can say as if it is along x. So mx whenever we are talking, then it will say along x. Now if that be the case, what we can do, this is your dimension b and this is your dimension d. Our objective here to resist this moment mx or m, whatever way, and p also, that axial load. So what we can do, we can increase the depth. So it may be preferable to use rectangular shape rather than square, because we have to resist this moment we have to resist. So obviously that this depth should be more. And also what we can do, shall we provide the reinforcement along this only, because then we are getting the maximum from the, because so far wherever you you put your that reinforcement, so far axial load concerned there is no problem, but so far the bending moment concerned, what we have to do, obviously since this moment acting about this axis, so what we can do, we can provide the reinforcement here, that means either at this end and the other end, that we can specify. Alternatively what we can do, if it is required, what we can do, we can specify the reinforcement all along. So obviously we are not taking the full benefit of this say reinforcement, only it will take the axial load, but for biaxial bending obviously you have to specify the reinforcement all along, that all in all the sides you have to specify. So this is the general case whenever you are considering that one, how shall we specify that. Now what our code says, I mean, how shall we start design. So far we know that how to design that axial loaded column, but how to design that one, say your uniaxial bending, let us say. So uniaxial bending means axial load plus moment about one axis, or moment about say major axis I can say. So moment about major axis and axial load, if that be the case, then how shall we design? In that case what we do, if we come back to the strain diagram, so this is your B, D, I have told that somewhere, if we draw the diagram, so we have somewhere 0.002 and 0.0035. I repeat once more, this is very, very important. So this is your stress and this is 0.446 after the material and all other say your say partial safety factor, we can get 0.446 FCK. Here what we shall do it here, somewhere we shall get here so we shall get 4/7D and 3/7D, and we have at this point we have 0.002 the strain. What happens here, this is our pivot point 0.002, and from the highly compressed area, because we are talking this one, say this is the highly compressed zone, this side, that compressed highly compressed fiber here. So what we shall do, we shall start, it may happen say something like this. If this is 0.002, then this one 0.0035, please note this is point, because this is as per that it is satisfied, and this one 0.002, 0.0035. Our objective here, this case, what we shall do, we shall find out one case that it will be pivoted with respect to this point, this line, as if I am considering. So this is your neutral point right now, this one will be with respect to this point. So what we can do, somewhere I shall get like this. So neutral axis is going outside the section, this one neutral axis is going outside the section. What I am trying to say, the bending moment, we have the bending moment and we have the axial load and bending moment. I know this is the critical point here at 0.002, this point. What I am trying to say here, with as if with respect to this point, this line is being rotated. In other case, this is your neutral axis right now. So if it rotates, it will never go beyond 0.0035. So that means what will happen, it will try to rotate about this point. At some other point it may happen, say like this. What is happening then? It means that if I start like this, this is your point, say line, then what I am doing, as if I am rotating like this. So your neutral axis is going beyond the section and finally it can go to infinity, I can say. That means in that case it will be 0.002. The strain will be 0.002. That means when the neutral axis at infinite distance, then I can say that your strain is 0.002 and that is throughout the section. That is what I mean to say. So here what does it mean here? That means it will happen like this. In one case we shall get something like this. This is your the stress diagram. When the neutral axis is outside the section, then what will happen? It will happen, we shall get the same way this particular one. So I am getting which is going beyond this, so that means I shall get certain portion here. This is your that portion which is acting on the body, which is the part of the column. This portion will no longer acting because there is no section here. The column is only here, this portion, the D, but this portion there is no column. Compared to the your beam problem, there is no problem because we are taking the whole area, but whenever you are talking column, in that case, in certain cases and in most of the cases, it will happen that it is partially loaded, that is stress block will not get the full one, we shall get part because neutral axis is outside the section, and this area we have to calculate. So what is our objective here? Our objective here, that P and M we do not know, because since it is P and M there are two parameters, so we do not know in which case it is safe. Now what we have to do, we check it for different neutral axis position, we find out that P and M, how much moment and how much axial load it can take, that particular section can take. What is the moment of resistance and what is the axial loaded resistance for the axial load, that we calculate for a particular that neutral axis position. And then what we can do, we can find out that one and we can plot it, and that is called interaction diagram. So it is not possible directly the way we have computed so far, the deterministic way. Here we can say a little bit iterative. What you have to do, you have to draw the column interaction diagram. So what we do, we can say as if we are having P and we are having M. So in one of the cases it may happen that there is no moment, already we have done it. It may happen there is a moment, and in another case it is possible there is no axial load. The interaction diagram, it comes for a particular area of steel, then we are having say grade of steel, then we are having say concrete. What we do, that means let us choose a section, and then you find out the what is the axial load, how much it can take and how much it can take the moment. How should we find out? I shall find out that let us assume that this is the neutral axis position, that we can take it, and if we take the neutral axis position, on the basis of that we can find out how much moment and how much axial load it can take. Similarly, I can take another neutral axis position and again I can calculate what is the moment and what is the axial load. So in this way, if we just plot it, then we shall get one interaction curve like this, and that is for an area of steel, as we have assumed that we are getting one particular area of steel. Now if you change the area of steel, then I shall get another curve, say like this. If I do again change the area of steel, then I can get another curve like this. So if we get it here, then what we shall do, if P and M is given, P and M are given, that P and M given, then what we shall do, then we can find out from here that let us say that P is here and M is somewhere here. So, we can find out, then if I know the P and if I know M, because that is given, for that we have to design. So, if we know that one, then wherever it is intersecting, so that percentage of steel we have to take it. So, this is your, that way this intersection diagram is helpful. But what we do, and for that SP 16, that special publication 16, that is given the different charts. What we do it here, instead of that we make it PU, PU is the design load, and that we divide by FCK BD. FCK is the concrete grade used, B is the that width of the column, and D is the that you say depth of the column. So, PU FCK by BD, because I know PU, I know MU also, MU divided by FCK BD square. So, I can, if I, since I know PU and MU and I am choosing a section, here I am choosing a section, that means okay, let us try trial section, 300 by 300, 300 by 400, 250 by say 300, like that. Let us choose a section. If we choose, and I know that which concrete gauge has to be used, so I can find out PU by FCK BD and MU by FCK BD square. And that one here, instead of this P and M, because then it will be dependent on, because this one becomes non-dimensional, so that is preferable instead of having some absolute value. So, this diagram we prefer, instead of giving P and M, we give it as PU by FCK BD, because then it is dependent on any FCK, you can use it, and MU by FCK BD square. Then what we can do, since I can calculate these values, then I can find out here wherever you are getting this percentage of steel, and that percentage of steel also not given as directly P, instead of it gives as P by FCK, P by FCK. So, if I get that P by FCK, then I can find out percentage of steel. P means that percentage of steel divided by FCK, the which concrete grade you are using. So, that way we can find out. So, let us try one problem, then I think it will be clear. Okay, let us try one problem, then what I mean to say, that it will be clear. So, let us take one example. Let us say PU given say 1200 kilonewton, MU 250 kilonewton meter. So, PU and MU given, concrete grade M20, steel grade Fe415, clear cover (40 millimeter). For column we generally use the clear cover 40 millimeter. Now, whatever the E mean, will be equal to, then let us take for basically say unsupported length equal to millimeter, and it is a pinned case, and both joints are hinged. Okay, let us take this particular condition, so that we shall get the effective length also. L by 500 plus D by 30, This is the one. Let us take the column section. That could be say 300 by 400. This is millimeter, 300 by 400 millimeter. So what we can do, we can find out E mean. I do not know, I have taken 300 by 400, but I may have to change, because I do not know right now. We are thinking that okay, it may work. We can also choose other way also, that we can assume that P, on the basis of P also you can find out, and then back. But anyway, we have to try with something. So let us try. And then D equal to here 400 by 30, and which comes as 6.44 plus 13.33 to 19.73. So let us find out design for M. What is the mu by P? Pu? Mu by Pu equal to 250 into 10 to the power 6 divided by, which is 208.33, which is greater than 20 millimeter. So we have to design for M. Even mu is specified, even then if we check it that mu by pu is less than 20, then we can simply go as I say your axially loaded column. But anyway, it is quite high, so you have to design for moment. So what we shall do it here, mu and pu. So let us find out pu by FCK BD. Pu equal to 1200 into 10 to the power 3 divided by 20 times 300 times 400, which comes as 0.5. Mu by FCK BD square equal to 250 times 10 to the power 6 divided by 20 times 300 times 400 square, which comes as 0.2604 or 0.26 simply we can take it. What about the what about your D dash? Our code says that it is not only dependent on this pu by FCK BD, mu by FCK BD square. Since it is dependent on, let us say we shall provide the reinforcement along this. When you are calculating moment or moment of resistance, what is happening here? The strain in the steel, or in other words the stress you have to compute on the basis of the strain. Let us say this strain also you have to find out, and then you have to accordingly you have to find out the stress, and where it is at a distance d dash. What is d dash? D dash is the effective cover. So d dash is effective cover. Our code says that we shall not take this pu by FCK for just only one chart. Instead of that, let us make it for different, because depending on the d dash your strain also will change in the steel, and so your stress also will vary. So let us make few cases, and our code gives that d dash by d, that rather is a piece of publication they have computed, d dash by d, that is for 0.05, 0.1, 0.15 and 0.20. So since you have to calculate d dash, let us say we shall assume 20 millimeter dia bar. So d dash will be equal to 40, that clear cover, plus 20 by 2. which comes as 50 millimeter. So our D dash, that is 50 millimeter, because here also again I have chosen that 20 millimeter, because I do not know whether 20 millimeter will be sufficient, because it may happen that I have to increase or decrease that one depending on the, say, your area of steel computed. So we are taking here also, initially also I have taken a section, I do not know, but anyway that is a trial section. Here also I am trying with 20 millimeter dia bar. So D dash by D equal to 50 by 400, and which comes as 0.125. Now let us show what we have. We have D dash by D, then we have PU by FCK BD, which is equal to, say, 0.5 that we have computed, MU by FCK BD square, that also we have found, that is let us say 0.26 only, let us take 0.2604, though we have computed. So this particular one. So we have to find out the area of steel, and this, from this special publication, what we can do, we are having so many. If you see this side, actually it is written that steel grade, here it is Fe415. Okay, just only to mention this one, let me tell you. So we can get it here from chart 31. Please note down chart 31. Just to make it for reference. So chart 31, page 116. This is for Fy 415 Newton per millimeter square, and D dash by D equal to 0.05. Similarly 32, 33 and 34. So 32, the same one, this is in page 117, page 118, page 119. This is for same one. Only change is that D dash by D, this is 0.1, D dash by D 0.15, and D dash by D 0.2. So we are having these 4 charts specifically for Fy415, Fe415, and for different D dash by D. What we can do, we have 0.125 D dash by D. Now one can say that 0.1 and 0.15. Let us find out from these 2 charts what are the values. So if D dash by D .1, P by FCK from chart 32 will be equal to, which comes as, it is difficult, but anyway just let me tell you, this is the one, that chart, how it comes. You can say all of them, these are all coming. This is from, say, 0, 0.02, 0.04, that is P by FCK, percent of steel divided by the grade of concrete. So different one we have. Now we have, what is the value we have got, that is 0.5 and 0.26, and this is for D dash by D equal to 0.1. Generally it is written here D dash by D 0.1, and little away, that is your, say, here, that for 415. Okay, it comes in this fashion. So what when we can do it here, we can find out 0.5, this is 0.5, okay, just to tell you this is 0.5, and we have 0.26. So 0.26 is somewhere here. So wherever it cuts, it will cut somewhere this value, and that value we have to take it, that P by FCK. So which is coming as here 0.5, this is 0.5, and I have told 0.26, please bear with this one just to tell you that how it is coming. Okay. So somewhere it comes somewhere here, and as per my, that is actually it comes between 0.2 and 0.22. Please know, just to refer this one because it may be difficult, but only to tell you that chart 32, and you have to find out pu by FCK BD in this direction, mu by FCK BD square in this direction. If you just get, you will get a point, you will get that P by FCK. If it comes in between, so you just from the I estimation you find out that what is the value. So if you get it, so I have got it here, P by FCK equal to 0.218. Similarly, the other one also, d dash by d equal to 0.15 and P by FCK from chart 33, which comes as 0.24, because d dash by d 0.1, d dash by 0.15. Now one can argue, so which one, obviously if we do not interpolate, that means because our d dash by d which we have computed, that one equal to 0.125, d dash by d equal to 0.125. So if we do not interpolate, then obviously we have to go that chart for d dash by d equal to 0.15, because percent of steel here more. So let us take this one itself. Let us do not interpolate. So let us take this particular say chart 33, and we can find out, because that we will be in the conservative side, because we are not doing an interpolation. So what we are doing, so we are just simply taking say from d dash by d 0.15. So we shall always take the higher one, and then we shall get that 0.125. So let us find out how much is getting. It is 0.24. So we can find out P will be equal to P by FCK equal to 0.24. Therefore P will be equal to 0.24 times 20, which comes as 4.8. So if we get this particular one say 4.8 percentage, so it is quite high. I generally do not prefer this much of steel. Anyway, let us find out what is the difficulty, how it can happen, that one. So 4.8%. So P equal to 4.8%. Let us find out that what is the difficulty we will face. So area of steel equal to 4.8 by 100 times the section 300 by 400, sorry 300 times 400, and which comes as 5760 square millimeter. Area of steel, that 20 millimeter dia bar, that which we have assumed that we shall provide. Area of steel of 20 millimeter bar is 314. Okay, and number of bars will be 5760 by 314, 18.34. That means at least we have to provide 20 numbers. So 20 numbers, 20 torr, that we have to provide. Let us find out, and we have assumed, because we have taken a section, please note, we have taken a section, I think you could find out that we are providing the reinforcement in only in the two sides, not all through. So this one we have chosen, that means now we cannot provide that all through, that these 20 number bars we cannot provide in all through. So that means what we have to provide? We have to provide the reinforcement along this. So 10 numbers this side, 10 numbers this side, like this. So what are the difficulties here? Let us assume that we shall provide 10 numbers. So 20 times 20, 10 times 20, it comes here, so 10 times 20, which comes as 200. 10 times 20, which comes as 200 millimeter. So what is the that means how much you have to provide here? This distance, this is 300, and that is called detailing. Whenever you have to provide the reinforcement, this detailing you have to consider. So if you provide here 300, so 300 minus clear cover, minus we are coming to center, so 25 by 2 minus 25 by 2, which comes as, so 20 by 2, yes. So which comes as 40 plus 40, 80, 80 plus 20, 100, so which comes as 200. So that means the bars simply we have to provide along that, we shall not get any space. So where will that coarse aggregate, all the aggregates will go? That means how should you do the concreting? That is the difficult point. So always you have to consider that this particular one you have to consider. Let us assume that we shall provide say 25 millimeter. The bar diameter say 25 millimeter. If we provide 25 millimeter, then also is there any difficulty? Let us find out. So 25 millimeter bar dia. So area of steel of each bar equals, this one will be 491, right? So area of steel, that one will be 491. So how much your steel, number of bars? So 5760 divided by 491, and which comes as 11.73. Number of bars, that means 12 at least you have to provide. So 12 numbers, 25 torr. So what happens here? One, 2, 3, 4, then 4 more. Now we have 300 minus 40 minus 40 minus 25 by 2 minus 25 by 2. So we get here 195. Okay. Now 195 divided by 1, 2, 3, 4, 5. There are 5 gap. So 39. So if it is 39 millimeters, so clear space, how much will be the clear space then? 39 minus 25 equal to 14 millimeter. So clear space between the two bars, we are getting 14 millimeter. Okay. So far so good, at least I can say compared to that. Let us find out what our code says. So let us find out what our code says, and that we shall get it in clause minimum distance, minimum distance between individual bars. Our code says in clause 26.3.2, page 45, IS 456 2000. Our code says, let me read it. the following shall apply for spacing of bars. Following shall apply for spacing of bars. A. The horizontal distance between two parallel main reinforcing bars shall usually be not less than, please note, shall usually be not less than the greatest of the following. So, whatever we shall get it, out of that we shall select the maximum one, and that should not be less than that value. So, the diameter of the bar, if the diameters are equal, in this case diameters are equal, in this case diameters are equal. So, which is here say 25 millimeter, we have taken so far, but even then that our calculation is still wrong, because d dash by d, that one also changed, all those things. But anyway, for the timing let us take 25 millimeter. So, spacing of bars. So, we are getting bar diameter, let us write down bar diameter 25 millimeter. Number 2, the diameter of the larger bar if the diameters are unequal. Sometimes we provide say 60 millimeter, 12 millimeter, 20 millimeter, 25 millimeter. If all the bars are not equal diameter, then we have to take the larger one, that we have to take it. But anyway, that case does not arise here. Here that case does not arise, because we are providing that 25 millimeter one. Number 3, 5 millimeter more than the nominal maximum size of coarse aggregate. So, whatever the coarse aggregate you are providing, so you add 5 millimeter more. That means, in our case coarse aggregate maximum size generally we provide 20 millimeter. The size of that maximum coarse aggregate size, that is 20 millimeter. So, you have to make 20 millimeter. So, coarse aggregate, that 20 millimeter, we generally provide say 20 millimeter downgraded, generally we describe the aggregates. That means, it means that the coarse aggregate will never be more than the 20 millimeter. So, 20 millimeter plus 5 millimeter, so which is coming as 25 millimeter. So, what is the spacing then? Out of that obviously it has come 25, 25 both, but anyway out of that, if which one will be the maximum, that we have to choose, and it should not be less than that. But in our case what happened? In our case we have got it only 14 millimeter. That means, with this section we cannot provide, so we have to increase the section. So, that also you can find out here also. I have told you that percentage of steel P 4.8%, whatever you have got it here 4.8%, that itself is alarming. That means, you need not go to that level just for your academic exercise I have written here, but in actual practice here itself, that is why I restrict that one, say maybe say 3% or less than 3%. So, if you restrict that one, immediately those things could be taken care of. Okay. So, we are getting 25 millimeters. So, what we shall do then? Then we shall change the section. So, let us change the section. So, let us take so 350 by say 450. So, we are taking the section say 350 millimeter by say 450 millimeter, that section we are taking. So, what will be then Pu by FCK BD? That 1200 into 10 to the power 3 so which comes as 0.38 mu by FCK BD square. $250 so it comes as 0.38 0.176, let us say 0.18. What about D dash? D dash equal to say 40 millimeter. Let us take bar dia, because we have seen that 20 millimeter is not the good choice. Let us take 25 millimeter. So 25 by 2. So we are getting here 52.5. So D dash by D equal to 52.5 divided by 450, which comes as 0.116. So what we can do then here, that section we can take it, that chart, the chart we can take it here. I think the chart, corresponding chart we can take it here. Let me find out that one here, 11, 12, yes. So 0.116, that is D dash by D, and we can come, so 0.15 directly we can take it 0.15. So what is coming here 0.15, your 0.38 and 0.18, just let me take it here because it will be difficult, but only for your reference I am talking. So which comes as here point, say approximately I can say 0.135. So P by FCK 0.135 from chart 33, page 118, for D dash by D equal to 0.15, for D dash by D equal to 0.15 that we have chosen. I am not doing any interpolation, so I am a little bit in the conservative side. So P equal to 0.135 times 20, so 2.7. Okay, I am happy at least it is less than 3%. So area of steel equal to 2.7 by 100 times 350, that section I have chosen, and times 450, which comes as 2.7 into 350 into 450 divided by 100. So 4252.5. Number of bars, let us take say provide 25 torr. So 4252.5 by 491, 8.66. So we shall provide 10 numbers 25 torr. Okay. Now let us check that whether we have got that that clause, whether it is violated or not, that we have to always check. So we can find out now. We can find out now here 1, 2, 3, 4, 5, 6, 7. So total 10. So we are getting here, this is 350 and this is 450. So 350 minus 40, clear cover this side. So this one also D dash, minus 40 minus 25 by 2 minus 25 by 2. so which comes as, so 105 to 245 millimeter. How many gap, number of gaps? 4. So spacing center to center 245 by 4, so 61.25. Clear spacing, so 61.25 minus 25 by 2 minus 25 by 2. So we shall get it here 36.25. So which is as per the code, now it is not violated. So we have enough gap, because we have to provide that once a course segregates. So that's why it is very, very important in your say reinforced concrete design, that your say clear spacing, all those things, that is detailing, that we have to specify. Okay. So let us conclude at least this particular class today now. We shall continue in the next class. Okay. So thank you.